Hello, my dear students, and I am here to do a quick discussion for our virtual students who did not get to stay and work together and discuss the lab that we did regarding properties of water. We did a number of properties of water and a number of quick little labs that, in my opinion, a lot of you should have done already. I'm going to open up our Google Classroom and show you what I'm working on. I want to give you the discussion and the background you need to complete this assignment. So if I go to our assignments, classwork in the Google Classroom stream, I have 3 labs. And those are properties of water lab here and more properties of water lab here. So I'm going to do the properties of water lab here. And we also have a properties of ice lab that we did the day after our ice day that we had previously. But I haven't had a chance to actually videotape that lab, let alone the discussion. I will prepare a discussion, but I'm going to have to videotape the lab when I can get back to the lab and videotape it. Of course, my plans were upset when we basically were not able to leave the house for the past week. So let me do properties of water lab. I'm going to open it up. If you click on it and open it up, you can see and follow along with me and answer your questions. Now, I will say I'm working from a teacher's perspective in Google Classroom, and I'm also working not on a Chromebook, but on my iPad. So I'm going to go ahead and close this down and open it back up from a file so I can be in a program, an application that allows me to use my Apple Pen. It doesn't seem to work inside the Google platforms. And I'm going to go to our water station lab. Let me make sure I have the right one. And this seems to be it. Let me make it a little larger. It is What's So Special About Water. Nope, this is the second one, so let me go to the other one. So a lot of the answers are inherent in both what I've written here, as well as what you observed when we went through and recorded the lab. But it says, predict how many drops you'll be able to put on the penny before it overflows by asking several people in your class. And I took a picture of the guesses from our class. And if you'll excuse me, I will leave this for just now. And I will go to my photos here. And if I scroll up past my snow photos and my photos of my kids and my granddaughter, there should be one here of the board, but I don't see that it's updated from my phone. Yes, here it is. So these are the guesses I had: 10, 5, 1, 2, 20, 7, 4, 5, 3, and 3. So if we go ahead and write those down, it says write these guesses below. Someone said 5, someone said 10, someone said 2, someone said 7. 2 people said 3. Oops, that should be a 3. 3. Let's see. One person said 1. One person who's probably done the experiment before said 20. And someone else just said 4 or 5. And so, it looks like an average of about 7 or so. But when we actually did it to see how many drops we got, we saw that thanks to the cohesive properties of water and the nature of water, a surprising amount of water can be placed on a penny as it forms that big bead of water, just like beating up on your car after you wax it. So I think a good average that people got was around 25 or 26 drops. So we'll put that. And the number of drops is different from our prediction because most people don't think of drops adhering and coalescing into one another. That means joining up and holding strongly to one another. But our results in terms of cohesion are such that a large, let me just see if I can write with this, a large number of drops can be put on the penny because water molecules are polar, and thus the two sides, the two poles, the positive and negative poles, attract, and the water has a property we call cohesiveness, but the water is cohesive and will stick together because water molecules are polar and stick to each other, bond to each other through hydrogen bonding. Each other. I don't have much room to expound anymore, but it says, do you think you'll get more or less drops? And I'm going to go ahead and take an educated guess because I know the properties of alcohol. So you will get I'm having trouble writing. You can put less drops of alcohol on a penny because alcohol is not so polar as water and forms fewer hydrogen bonds. There is some polarity in the alcohol, but there's also some methyl and methylene groups that, some carbon and hydrogen groups, so named, that themselves are held together only by dispersion forces, which are much weaker than hydrogen bonds, if you remember from our lecture material. So you can put less or fewer drops of alcohol on a penny because alcohol is not so polar as water and therefore doesn't form as many hydrogen bonds. I'm not being able to write because I'm trying to lean my hand on there, but when we did this, we got, actually a lot of people got up into the 30s with their drops of water, but we got 20 drops of alcohol. That was a good average. That's what I got. I'm just giving you my data. Now, what happened when you touch the capillary to the drop of water on the slide? Water basically jumped up into the capillary, rose up into the central core, the tube, into the capillary pipette, and it did so because water, in addition to sticking to itself, tends to stick to many other substances. When it sticks to itself, it's called cohesion. When it sticks to something else, it's called adhesion. And when we measured it, when I measured it, different people got different results, but the capillary dye traveled a little more than a centimeter. In fact, it traveled 11 millimeters. And then that's a pretty good distance. That's about that far for the water to rise. It wasn't pumped up, it wasn't sucked up, nothing happened except that the water just rose up in the capillary, and that's because it was adhering to the side of the glass, and it was cohesive with its own water molecules, or with other water molecules, and so pulled them along. But it doesn't go all the way up the capillary, because at some point the weight of the water column is greater. And remember, weight is a force. So you may or may not remember this from physics or physical science. Weight is equal to the mass times the acceleration due to gravity, g. And so weight is a force as we define it in a chemistry classroom. So at some point, that force becomes greater than the force of the hydrogen bonds. At some point, the weight of the water column is greater than the forces holding the water molecules together. The forces, or the force of the hydrogen bonds. The hydrogen bonds holding the water molecules together and to the glass. So, they can't overcome that force of the weight of the water column. So, inside the capillary. Very simple. We're almost done. Read the volume of water in the burette, and what measurement would you see? And when you measure this, okay, we had this not capillary, but burette, long burette. They're, several, 600 or 700 centimeters long, almost a meter long. But the water level, if you look at it, forms a crescent shape inside there, so that what we read is, from the bottom of the crescent when we're looking at it. If I'm looking at it, this is me looking at it, I try to get it at eye level. Okay, so when I looked at it, it was at 31 milliliters. And what we want to avoid is parallax view. And parallax view, I just happen to have looked it up in context, but if you don't view an object straight, and it's especially important in things like hunting and astronomy, where you're focusing on objects that are far away, if you move your eyesight out of the line and look even a little bit away, I'm going to go up here, and here's the Earth, and it's rotating around the sun. If I can draw a sun, I'm having trouble with my pen, and it's not rotating, it's revolving around the sun, and I'm looking at a star up here, okay? And that star is going to stay in one place, but I'm not going to know exactly where it is relative to the other stars unless I know distance. But in the old days, and to an amateur astronomer, you can't really tell distance. You can only tell its direction. But if I look at it, if this is summer and this is winter over here, if I look at it in the winter, that star looks like it's moved position and is over in this group of stars. That's called parallax. You want to look straight on to determine true position. And it's the same with this meniscus that we're reading, the curved surface of the water due to surface tension, due to adhesion of the water to the glass. And again, it's gravity that limits how far it will go. And of course, the strength of the hydrogen bonds to the substance we're adhering to. A plastic tube will have a slightly different meniscus than that, but if you look at our thermometers, they have a meniscus. If you look at a mercury thermometer, it actually kind of has a negative meniscus. It has a pillow top. But if I look at this from up here, if I'm too high, there's my eyeball, or my eyes, and I look at them from up here, I'm going to get too low a value down here. And if I look at this meniscus from down here, these are my eyes again, and I look at that meniscus, I'm going to get too high of a value. So if I have what's called a parallax view, it will not work. So parallax view in our case, let me just show you what I've done, is if I go back to my photos here and go to my view, that's meniscus, that's not what I want. There we go, parallax. Its formal definition is the effect whereby the position of directional object appears to differ when viewed from different positions. So we're viewing something from different position, and especially that of a star viewed from different points, as they give an example right here. Okay, so oops, my pen is not writing; it's moving things. It's acting as a pointer instead of a writer. But so the parallax view is a change in position that differs when you're viewed from, a change in appearance of an object when it's viewed from different positions. So for our purposes, it's a change in measurement, in a measured value, measurement. So our value, our measurement changes when viewed from different positions. And that is why when we do a titration and we are using these burettes later in the semester, we need to make sure we view them from the level of the bottom of the meniscus and that we're parallel with that. And then it says, what is the root and origin of the word meniscus? And as I've already shown you, I looked that up. And if you look here, you'll see here that it's from the Greek mene, which means moon, because it looks like a crescent moon, or meniscos, the Greek meniscos, which runs, which is again from the Greek, which means crescent, and the modern Latin is meniscus, so we're actually using a Latin word with a Greek origin. It means crescent, and by the way, the plural is not meniscuses, it's menisci, just like radius and radii and hippopotamus and hippopotami, you have meniscus and menisci. So its actual origin is the Greek from and means the word moon. So let's answer our question now that we've done our research. The root and origin of the word meniscus is mene, meaning moon, and some sort of Latin and Greek meniscus, spelled with like a K instead of a C, meniscos. I'm not going to go back and look it up, but meniscus is Latin, and then it was previously Greek, meaning crescent, or from the crescent moon, just like a crescent roll. They are crescent shaped. So that's our obligatory science of reading, looking up word roots and word meanings. So the conductivity meter, when we put it into pure water, nothing happened. It did not light up. A current was not carried in water. And it says explain. So, water, though polar with opposite charges on opposite sides of the molecule let's put it this way. Overall, water, though polar with opposite charges on opposite sides of the molecule, is uncharged. Overall, there's no charge on water molecules. Is uncharged and will not conduct or carry electricity or conduct a current. So overall, water is uncharged and will not conduct a current. Even though it's polar with opposite charges on opposite sides of the molecule, it's uncharged. And then when we put it in sodium chloride, it did carry a current. So sodium chloride NaCl, that's an A, by definition is an ionic compound that will conduct a current when molten or dissolved in water. So these are properties of water I think everybody should see and appreciate. I wonder if I can move this out of the way. There we go. And it says we put it into sucrose. And though sucrose is polar, that's cane sugar, just table sugar. Though sucrose is polar, it is uncharged. It has little areas of charge, but overall, there is no charge on sucrose. So it is very polar and will form hydrogen bonds, but though sucrose is polar, it is uncharged and cannot carry a current. Cannot conduct a current or electricity. That concludes our discussion and the type of answers I'm looking for this lab. I want you to, if you haven't done it, if you're face-to-face and you did the lab, there's no need to view it, but the virtual students really need to view the lab and see these phenomena related to water. It's an amazing substance, and it is the solvent of life, and we owe our lives to liquid water. No life would be possible were it not for water and its special and unique properties. I will complete the next lab report and post that soon after you see this one appearing. So until then, goodbye now.